welcome everybody. We have in store an interesting conversation here. This is one that I've really wanted to have for some time, and it's quite a niche that finding people who actually know what they're talking about is not particularly easy. It's quantum computing is the topic. I think for AI to achieve all of its promise, we're going to need much better computers. And whether that ultimately is quantum or what comes next, quantum is going to be a huge bridge to go from where we are right now to where you all probably think we are already. The general public, I think, has this misconception of where we are with respect to AI technology. And to get even as far as the public thinks we are, we need much better computers. So before I go any further, let me introduce the panelists, and I'm going to ask them to further introduce themselves, because I do think it'll be important for you to know a little bit more detail about their background so you know from which angle they come. But we have Robert Plotkin, and Robert is the founder of BlueShift IP. He's also written for us on IPWatchdog. He is also an author. His was it Genie in the Machine? Was that your first book?
Genie in the Machine was the first one.
And, and I've known him since that came out, and that's now almost 15 years old. It's hard to believe. And he's got several other books. His most recent book published within the last 6 months, really, I think, and about artificial intelligence specifically. He does this type of work, and we're always happy to have Robert here. Thank you, Robert.
Thanks.
And then next is Sarah Schlotter, and Sarah is an attorney with Wolf Greenfield in Boston, and Sarah is also a PhD. She holds a PhD, and she knows the quantum stuff inside and out from she's a technologist in addition to a lawyer. So she plays a lawyer, but she knows the technology like she's an inventor. So really happy to have you here, Sarah. Thank you for joining us. And Sarah, you want to try and explain what this is so that we have sort of a baseline?
Sure. You think of classical computing as being a discrete type of computing, right? You're storing information in a bit, a 0 or a 1. And as you store more information, you linearly need more bits. And those bits don't really talk to each other, right? You write them to a hard drive, they sit there, you're done. A qubit or a quantum bit, it can have a continuous value between 0 and 1, essentially. But you're mapping to basically a vector state. So you can encode into a broader, a larger sort of state and define your state that way. And instead of being a discrete value, it's beholden to statistical quantum physics. And the interesting thing about qubits is that they don't live in a vacuum. Well, they physically can't be made in a vacuum. Hardware-wise, but they talk to each other, right? They can be entangled through quantum entanglement. And so as you want to store more data, instead of scaling linearly, they scale exponentially. So 3 qubits gives you a lot more power than 3 just bits. And so it's really controlling how these qubits talk to each other that is the big trick of quantum computing.
So Robert, go ahead.
Yeah, and I would say, in addition, I would say quantum computer is one that leverages the quantum properties of the qubits, because you could say, well, a classical computer contains quantum properties within its electrons, but a classical computer doesn't leverage those properties to perform computations. The software isn't written to take advantage of the quantum properties, whereas in a quantum computer, the computer is designed to take advantage of entanglement and superposition, and the software is written based on the assumption that those properties are leveraged or exposed.
This is sort of the same thing like where a particle can exist in more than one place simultaneously, right? That's kind of the level of physics that we're talking about that goes into these machines, right?
Exactly, yeah. I mean, a lot of what I work on is when you entangle states in these qubits, they're not next to each other. They're in totally separate parts of the quantum computer, but they're talking to each other. Like their states depend on each other, and so it's very sci-fi.
What I'd like to do is let's dial it back a little bit and talk about why is it that quantum computers are necessary for the evolution of AI? Why can't ordinary computers do what we need to have done? maybe another way to think about this is, what is the particular advantage of quantum computing versus classical computing power?
To build on what Sarah said when she said that a quantum computer, if it were big enough, could contain and process exponentially larger amounts of information with a given set of bits than a classical computer. So the hope or the hypothesis is that we could get to a point where you could have a quantum computer that's large enough to process the same amount of information in exponentially a shorter amount of time, or conversely, exponentially larger amount of information. And from what you all know about where AI is heading, it's all based on training models based on massive amounts of information, often simulating large amounts of possible outcomes, performing optimization processes, which involve just massive amounts of computation, that when you want to do things like fluid dynamics simulation or weather simulation or any other kind of simulation of a physical system, that already far exceeds the best supercomputers. And so the hope is that we get to a point where we could make use of these quantum properties to tackle those problems. But it is unknown, one, whether we will be able to do that, and whether just existing supercomputers will be able to get good enough to do that, perhaps at some point, perhaps with some combination of better algorithms.
Mm-hmm. So Sarah, anything to add or expand upon?
I mean, I think there's quantum combined with AI is still very much an open research question. And so it's, what do you mean by better, right? Is it a quantum speed up? Is it using less power? Is it being able to solve a problem that a classical computer just physically cannot? In terms of speed up, I don't think we've yet seen that. There's some recent work that came out, I think from Honda Research, that they did image classifying with the same accuracy as a classical computer could do. I don't know that if you're going to do the same task that a classical computer can do, that you need a quantum computer. So it's going to be finding the use cases that very specifically need quantum computers, or where quantum computers can provide a really big, powerful speed up and save energy, time, what have you. And I don't know that the space has been sort of mapped fully.
So is this sort of like cold fusion at the moment?
In my opinion, it's similar, yeah.
Mm-hmm. Yeah. So we think eventually we're going to be able to do it, and we think it would be wonderful if we could do it, but there's still open questions.
Right, and where there are some useful applications, but on a small scale now, when Sarah said you have to find the things that a quantum computer is good at, people often use the analogy of existing computers with a central processing unit, a CPU, and a GPU. And the GPU, originally, they were used when for being really good at graphics processing. Now, of course, we know they're also really good at doing AI processing, but they're good at a very specific kind of task. And the way that they're used is in combination with the CPU. And that's for now, and possibly forever, how quantum computers will be used. We'll find specific specific tasks that they can perform well, and in combination with a classical computer, they'll work hand in hand to do something better, perhaps, than the classical computer could do on its own. And that just wouldn't be possible to do with only a quantum computer.
Mm-hmm. So going to the use case, what use cases are you seeing? And feel free to take it, one, generally speaking, and then two, what use cases are you seeing your clients, or the things that you, maybe if not your clients, but others have been filing at the office, patent office, that is?
Yeah, for my clients, it's largely, my quantum clients tend to be more academic or academic partnered. So it's very fundamental research. And the machine learning and sort of computing applications that I've seen are mostly related to drug discovery, molecule design, and to some extent clinical research trial analysis of the data coming out of clinical research trials.
So all the quantum applications I've done were for pure quantum software. I haven't worked on any quantum hardware applications. So some of them were for error detection and correction. because for various reasons, quantum computers are noisy and they're prone to errors, and so decreasing or eliminating those errors is extremely valuable. I also worked on applications for machine learning using quantum. As I said, optimization using quantum. Those are really compute-intensive fields that can benefit from quantum. And I'd say almost all of the patents I worked on were for hybrid classical quantum applications, where there, and we may show an example of a claim even, but where there's a classical computer doing the control of the quantum computer, essentially like a CPU and a GPU, sending the quantum computer certain tasks to do, reading out the results, and engaging in some sort of a loop.
How is the office doing examining these types of patents? I mean, does the office have like the most advanced quantum computing geniuses in the examiner art unit?
I wish.
Yeah. And not to, as I said that, I'd be like, okay, neither of them are going to want to answer that question the way I asked it. And it's not to say anything bad about the examiners, right? I mean, this is sort of a problem that comes up at the office, in particular, whenever there's a cool new unexplored technology, is the office has to find people who can examine it, but they don't know any more than most people know. And it takes time for them to ramp up, and that's where they have a lot of partnership meetings and training and so forth. Is that process going on with the office now, where industry's coming in and training examiners, talking to them?
I had one client, it was Zapata Computing, but they were a big client for me. We filed about 100 patent applications, got about 30 grants in the US and in other countries. Over, of course, about 6 years. They were a startup, they made a go for it, and they ran from 2018 until late last year. And I'll say, I didn't, still, at the end of all that, I learned so much and still feel like I don't understand quantum computing technology very deeply.
And when you get into quantum physics, right, I still struggle with just the basic, I guess I believe it because Einstein said it, right? But how is it possible that a particle can exist in two places at the same time? You know, that I have trouble in wrapping my head around based on our real world experiences. But in the quantum world, it feels like you almost have to pass through the looking glass and take a lot of things that don't make a lot of sense at face value because it works.
Yeah, I think the physicists that I work with, and in my experience, they put a lot of weight in the math, and they're like, well, this just falls out of the math. And so obviously it is that way. Which when you're writing a patent is not helpful.
And as long as there's no mathematical errors.
Well, yeah, that too. So to answer your original question about the examiners, though, I think the problem that I've faced is that I never see the same examiner twice. And, you know, we were talking about art units that we see our applications go to. It's across 2100, 2800. I think you also had a few others.
Maybe, I might have had some 2600, I'm not sure.
But you know, it's always a new examiner. They've maybe seen another quantum case or two. And we should, you know, quantum computers aren't implemented in the same way. There are multiple modes of implementing the hardware. And so even if the examiner has seen a quantum computer, maybe it was a completely different hardware implementation. So they may not even understand how your quantum computer works. So there's just a lot of education that you have to do when you talk to them.
I mean, one interesting thing I remember coming across is a lot of the software applications strike me as similar to chemical applications. Like we had at least one, maybe two cases in which the examiner found some prior art. I think he probably didn't understand the technology too well, but you know, he did pattern matching on the prior art, and we had some quantum set of data that had, I think, 3 units of data within it. And he found something that had 2 and said, well, it would be obvious to go from 2 to 3. And I didn't know any better, but I worked with the client, and they explained to me why it was not at all obvious to apply this knowledge of the 2-unit quantum structure to 3. But that's where when I say that's more similar to what you would often see in a chemical case, where you'd say for a chair, maybe something that has 4 legs would be obvious to make it have 5 if it doesn't convey any additional functionality, but that's not true with quantum. So it's strange in a lot of ways, and one of the ways, someone will know whether it's Richard Feynman who said, look, we just cannot look for real-world analogies to how the world works at the quantum level, right? In classical physics, you talk about pool tables with billiard balls bouncing around, and you can imagine what systems look like, and you just can't on the quantum level. So there's a lot of education. Zapata did go to the patent office twice as part of the examiner technical training program and train examiners. I found generally the examiners were very open to learning on a case-by-case basis. That was just my experience. They wanted to know, they were willing to admit that they didn't know, much more so than in software, generally. And I think we talked when we were preparing, like, we don't know, maybe that will change at some point. I don't know, but I did find that they were open to learning.
Yeah. So I wanted to go down the abstract path as well. I mean, do you guys see 101 rejections in this space? If you do, how often?
I've seen them fairly often. We with Zapata had a really good track record of being able to overcome them, usually by arguing, sometimes by putting in something about the physical transformation that happened in the computer at the qubit level. We had I think I have it in a slide, an appeal that we won on a 101 issue. That was a bit bittersweet because it was decided after Zapata closed its doors, but it was 101 rejection, and we were able to argue that the claim recited a transformation, a preparation of the state of the qubit, and that was a transformation. And we were confident that, that's always a great position to be in when you have something that is both specific, but as a practical matter, not limiting, because anyone who needed to do the same thing would have to implement that transformation, and we feel that that's the position we were in on this. So yeah, it does happen. But I think a lot of these questions you're asking and the things we're talking about raise this issue, broad versus narrow, which raises a bigger question, up front for every invention. What's the protection you're going to get out, and is that valuable enough to go for? And I think it's a very hard question to answer because of the overall uncertainty about where quantum computing is going.
Yeah, I mean, most of my clients, I'm like, are you even going to be using this in 2 years? Unclear. When they come up with a new algorithm or something.
So help me understand, what are they thinking when they want to file a patent application? Is it that they're just checking a box because they think that that's the right thing to do? Are they doing this for investors, or are they doing it because they really think, 10 years down the road, this could be something, and then maybe there'll be infringers that they need to have an asset to go after?
I think for my clients, it's typically for investors, but it's also to sort of build a fence. Like, I've had them file and things are like, we would never actually do this, it kind of sucks. But I don't want anyone else doing it either. I'm not sure any of them are particularly interested in actually enforcing their patents. So I tend to go narrower, and so therefore I see fewer 101s in my practice.
Okay.
We did, for a variety of reasons, the ones that you mentioned. In some cases, we, or the client particularly, thought that that the invention was solving a problem that everyone in this small field was working on, which gave them some confidence that if we get a patent granted on it, it would be desired or be blocking to others. But it's just so hard to know. That's all I can say. It's a humbling field to work in because the technology is hard to understand. It's hard to know what it is. It's hard to know where the industry is going. It's hard to know where the technology is going. And as with all things like this, it's hard to know what the timing is. This could become big in a year or 20 years. And as long as a patent lasts, sometimes 20 years, we've seen other technologies where you think, I'll file now, it doesn't matter, because 20 years will certainly be enough time. And the market develops 35 years later.
Yeah, I mean, one of the great examples, Einstein predicted lasers, and they weren't made for another 50 or 60 years.
Right.
You know, you just never know when you're on these cutting edges. So, and the reason I asked specifically about the abstract stuff, obviously, it's relevant for software, it's relevant for AI a lot. I remember very early on in, you know, sort of the patenting revolution for AI. Somebody who was doing a lot of work in that space, she had a PhD in, you know, neurobiology, and she was just an extremely smart person. She would rant to me about getting 101 rejections from examiners, and they'd say it's abstract, and she would say, okay, so you understand the invention then. You know, and it's like the fact that it's abstract is what really makes it useful. It's the whole raison d'etre of AI is you don't know exactly what it's going to do. I can tell you how I've set it up to do it, but we don't really know exactly what it's going to learn, how it's going to learn, how quickly it's going to learn, what it's going to give us. And that's what makes it exciting and particularly useful. Do you have that same kind of aspect? I would think you would in quantum, that, you know, this is a build it and then we'll see what it does. I can tell you how I got this far, but the examiners always want to know, well, then what's the next step? What's the why? How are people actually going to use this? What's it going to be useful for? And I'm not sure that you have that answer for quantum right now. And I wonder how much that affects the 101 inquiry.
For me, I think I try to focus the application and provide a story on how this improves a quantum computer. It improves fidelity, which is like how unaffected by error it is. You know, it improves the length of time that the qubits can be stored, which, you know, makes it so that you can implement more complicated algorithms because they take time. And as long as you say those things.
So that's just straight and fish play.
Yeah, and it works great.
Yeah.
So, you know, I don't tend to go into those bigger questions because my inventors don't know. They're like, I've invented a new quantum operation. It could be used in so many algorithms. Like, they haven't even thought of what they're using
And the
for.
examiners are okay with that?
At least mine are. I mean, my claims tend to be very focused on the specific hardware, and it's like, okay, the quantum computer is applying this electromagnetic stimulation to cause a transformation of the state to evolve it to this second state that is desirable, and that's a very physical thing. So the examiners seem to understand that.
Mm-hmm. I would say the same thing. I try to avoid going there if I need to. If you look at this patent, right, looking back, I'm not sure I would have even used this title. You know, we all question our own choices, but, you know, it's a method for solving linear systems. That sounds very mathematical. And how did we overcome it? By focusing on the physical transformation that happens within the quantum computer to achieve the solving of linear systems. And that succeeded, you know, that succeeded. So wherever possible, I find it safest to go to how this is implemented in a physical system. Now, one thing I don't know is, will that keep working over time? I don't know. Well, there'll come a point, because we used to do it in software years ago, focus on what was happening inside the computer, and eventually...
Like there's a bunch of gates, yes, no, you go through zeros,
no,
right? Because they're all ones and zeros.
It drives me nuts when I'm talking to on classical software, and I'm like, well, but the hardware, like, you have a hard drive that is writing bits, like something is happening.
Yeah.
And that doesn't work.
No, not on the classical side.
But for a quantum computer, totally fine.
Let's go down that path a little bit more, though, because before I go down any further, let me take another stab at who the examiners are. Because there is no art unit, right?
No.
And not that an art unit matters nearly as much as it used to, given the way the Office assigns cases anymore, because they're looking for, on this application, where is the right person in the office that has the right knowledge base to examine this. Is that right person in this space coming from some of the AI art units?
Occasionally.
And where else are they coming from?
A lot of, for me, because I do a lot of superconducting circuits, it tends to be like solid state devices, microwave engineering, error correction, for even just digital error correction. Sometimes my quantum computers land there. I will say, in my experience, Europe has a specialized art unit that does AI and quantum together, and their examination makes a lot more sense. Like,
I would
just
think
what they
so,
write.
right? I mean, how could somebody? I mean, it's hard for all of us who are engaged in this AI stuff to wrap our heads around quantum computing in the way, nearly in the way that you guys have, because you've really peeled back the layers of the onion because you've had to, because clients and so forth. I can't imagine an examiner who's looking at classical telecommunication systems all day long is like, yeah, this is a quantum computer that will be used for telecommunications purposes. But that is not a prerequisite to understanding what makes this invention unique. It's the quantum aspect that makes it unique, right?
Right, right. In fact, when we say that the examiners generally are not that knowledgeable about quantum, on the other hand, I have to say I give them credit. Sometimes we would get 102 or 103 rejections, and we would say, oh, the prior art's not quite on point, but it was in the right ballpark. And could I have found something in the right ballpark? I can't say that I could have. So I have to give them credit for doing as good a job as you could expect in light of the fact that this was not in their primary field.
Yeah, so this is a question I need to get some clarification from the patent office on, because I know in years past, and this is like years and years ago, when they would have new technology areas like this, they would go looking for examiners who were interested, who wanted to be challenged that way, who were not going to be afraid of it. And I know, and unfortunately, he literally just passed away over the last couple of weeks, the first examiner who ever issued or examined the MRI. And they had quotas at the time, just like they have now, and he had production goals and so forth. And he went to his supervisors at the time and said, there's no way we could do this any justice whatsoever in the time that I have. And the supervisor, to his credit, told him, take whatever time you need, because they knew if this really does what the inventor says it does. And of course, we all know now that the MRI machine, it did what he said it did. It was revolutionary. And I know my friend, who many of you know, John White, he probably taught many of you how to pass the patent bar exam over the years. He had a similar experience. They couldn't find anybody who wanted to examine automobile transmissions, but that's his hobby. He's a gearhead, so he volunteered. So you go for some of these highly highly specific, highly technical, and to most of the rest of us, mind-numbingly boring. But it won't be mind-numbingly boring to everybody. There'll be people who really find it interesting. So hopefully that's what they're doing. We'll see if we can get some answers. But do you have anything more to say about the...
I remember, and maybe there's people, I'm curious to know if anyone here in the audience knows more about how the internal mechanics of the PTO works on this stuff. But I remember when nanotechnology started like 20 years ago, there was a lot of talk. There was talk of creating teams of examiners, from material science and physics and other things, because for the same reason, no individual examiner was going to have the technical knowledge to examine some of these nanotechnology applications, and it never happened. So it's an interesting problem. How do you deal with these cross-disciplinary technologies like this?
Mm-hmm. And I think the way that they're trying to do that is identify based on, and I think they might be using AI, I don't know, but they're trying based on this application. They grade it somehow, score it somehow. That's where I think the AI aspect of it comes in. And then they're also constantly looking at, and not grading isn't the right word, but rating, or which examiners have the highest likelihood of being able to tackle this application based on the applications that they've seen in the past. And I mean, I suppose if you're not going to put a multidisciplinary team together, that's probably the best way to do it. And with the backlog, I don't think we're ever going to see right now multidisciplinary teams examining a single application. So, and the reason I went down that path to begin with is I wanted to ask you specifically about what are the differences between the way the office handles AI examination versus quantum examination?
Just totally different things.
And why is that? Is it just the examiners? Is it that they feel more comfortable and familiar with AI, so they feel like they understand the technology better and a little bit more skeptical of the claims and what you've written in the spec, versus quantum that maybe they don't really, I don't want to say don't want to get it. I mean, I don't know that any one person really gets it. So it's not an insult to examiners, but they don't feel like they understand it as well as the AI just because of familiarity.
That's probably part of it. I think part of it, the differences I see are really in AI, you're getting hammered with 101. And in my quantum applications, it's sort of more standard 102, 103 issues. So I think, when they see AI, they're like 101 flags go up. And for quantum, it isn't necessarily the case that happens.
I agree. That's been my experience, and I think it's like a controlled experiment that shows you the problems with where 101 is now, in that we're seeing these two different technologies where you can write claims for essentially the same type of a method, and you get hammered with 101 if it's done by a classical computer, and not if it's done by a quantum computer, because you can point out on the quantum computer that it involves preparing a quantum state or something like that. Where, as we've said, if you put in language like that, like we used to do, signals on the classical computer or something evolving the state of the transistors, you'd still get the 101.
Right.
Which makes no logical sense to distinguish them that way, but that's where it is. That's where things are now.
I think what I've seen is as the field has matured, we're moving from strictly hardware to either combined or software only. Because now it's how do we use these things that we've built, right? Like the fundamental hardware has already been patented or disclosed. So it's like, what can we do with this thing that we've made?
The only thing I'll add is there are some applications, I know that we filed and patents we got granted for Zapata that would be analogous to maybe really low-level software back in the 40s, where you had fairly unreliable analog or early stage digital computers, and you were writing the super low level code to run on those processors and do things like low level error correction. People are writing that type of software. It's like firmware almost, maybe.
Yeah.
For quantum computers, and there are patents for that happening now.
That's probably the majority of what I do.
The question that maybe I should have led off with at the very beginning is, do quantum computers actually even exist? Or is this all theoretical? It's a funny question, right? But I'll tell you, the internet doesn't agree. There are people who are adamant that, the quantum computers, they just don't even exist. And then there are people who say, well, no, they exist. Can you build, I guess the question is now, can you build a quantum computer?
So I think the way it's defined is we're in sort of this era before the perfect, amazing quantum computer that can do everything that we want. So it's the NISQ era where they're still noisy and, they're intermediate in size, but they're doing quantum operations. So I would say we have quantum computers. They just maybe can't do everything that we dream that they would do.
Yeah.
So are they special purpose quantum computers? Is that sort of a lay way to understand what they are at the moment?
Yeah, I mean, they're small qubits typically, 32, 100. We're getting more and more qubits, so they only have so much processing power. And then they are subject to sources of noise, thermal noise, that can sort of derail the computation. So they're just not perfect, is where we're at.
Mm-hmm.
It's like saying, do we have AI? Sometimes when people hear that, they say, do we have AGI? That's what they hear. Well, we have AI, but it's still relatively primitive as things go, but it does exist. It's just not maybe equivalent to a human expert or to the things we imagine it being capable of doing, but it's there.
Yeah, so we don't have data from Star Trek yet, right? There's the robotic, all-knowing.
No, they're not magical yet.
Right, they're not magical, right? So, so they do exist, but probably, again, like with AI generally, they don't exist to the extent that a lot of people think that they exist.
Right, and I think like AI, the reason they're getting so much attention is that if the bet pays off, it'll pay off big time. Right, and so
particularly for security.
Yeah.
So why say that, Sarah?
Well, right. The idea is a quantum computer could just crack any encryption.
Oh, I see. So it's not like more. It's not that the quantum computer is more secure.
No.
It's that the quantum computer can make everything else insecure.
All communications, would be insecure. Which is why we have companies that are working on quantum telecommunications, which are then quantum secure. So it's sort of two races. Side by side.
All classical encryption relies on the difficulty of factoring large numbers, and
Which quantum computers are good at.
would be really good if they got big enough.
Yeah. Yeah, and I always tell people, it's like, if there's somebody that's good enough to make it secure, there's somebody that's good enough to make it insecure. It's just a matter of time. So it is a race, but it's like we talked about yesterday with AI. It's a race that is never going to end.